All right, guys, welcome to a new section. In this section, we're going to start with section 7.4. Okay, that's going to be the focus of our study, 7.4. And in 7.4, pretty much, we're going to learn about, we're still actually on chapter 7, which talks about integration, right? So right now in this session, we're going to learn about integration of rational functions. Okay, so rational functions by the so-called partial fractions. Okay, so I'm pretty sure that you guys actually learned partial fractions in the past when you took a class in college algebra. All right, so we're going to be solving integration problems by using the idea of partial fraction, split them up using partial fraction, then integrate. Okay, so the first thing I'd like to remind you guys are, what is a rational function? Okay, so it's safe to, start by defining this guy. Okay, so a rational function okay, this is a type of function actually. It's a function. It's given by this guy, okay, P of x over Q of x. So that means a rational function is a function such that you can write it as a quotient of two other polynomials or two other functions. Okay, so where the P of x and Q of x are actually polynomials. Okay, so of course, let me still remind you guys what a polynomial is. So a polynomial, all right, is of the form. Okay, how do we write polynomials, guys? In general, we write it like this. We have a sub n, x to the power of n, plus you have an plus 1, an minus 1, xn minus 1. Of course, you keep going, right? Then you have like a1 of x, then plus a0. Okay, that a0 is just a constant. All right, so and then you have an not equal to 0. Okay, let's an easy example is this. Suppose you have 5x cubed plus 2x squared minus 5, right? Minus 5x plus, let's put 3. Okay, so this is a polynomial, right? Of degree 3. Okay, so here, polynomial of degree 3. So, but in this case, we are just writing the general form. The general form of the polynomial is given by this guy. Okay, now the degree, how do we know the degree of the polynomial, guys? The degree of P, in this case, is just n. So pretty much that's just the highest power, of the x. So in this case, in this example I have here, I have 5x cubed. The next x was just x squared. The next guy was just x. So what is the highest is 3. So that means in this case too, the degree of my polynomial P of x is just n, because n is the largest. Okay. Now, so what's the motivation of actually studying integration by using partial fractions? Now, let me start by giving you guys an example, guys. Suppose we actually take, now let's have two functions right now, 2 divided by x minus 1, and we have 1 divided by x plus 2. Suppose we take this guy to a common denominator. Okay, so what does a common denominator mean? I just want to ensure they have the same bottom, right? So think about how you do, let's do 1/2 plus 1/3. If I want to add these guys together, right? What do? I want to make sure they have the same bottom. So, and to do that, in this case, I'm just going to have like In this case, I'm going to have, this is going to be a 3 over 6, right? Plus 2 over 6. And then this becomes 5 over 6. Because right now they have the same bottom. This is 6 and 6. I can sum up the power. Okay, so we want to apply the same principle to this guy. So, okay, so suppose the operation in this case is just subtraction. All right, so suppose we just want to subtract them. Minus, in this case, 1 over x plus 2. If I need this guy to have the same bottom, guys, remember how we do this becomes 2, right? Divided by x minus 1 is x plus 2 divided by x plus 2, right? I introduce that guy. Minus, you do have a 1 minus. Sorry about that, guys. Okay, so 1 divided by x plus 2. And this is x minus 1 over x minus 1. Okay, so pretty much it doesn't change anything, right? Except the fact that it's just a way to introduce the same thing on the bottom. Because pretty much this guy can cancel this guy. This is just going to be 1. So this guy times 1 gives us the original thing. Okay, so this is going to be, of course, right now they have the same bottom, right? This is x plus 2 and x minus 1. This guy is 2, x plus 2, right? Minus, after this minus, you want to have a parenthesis. Okay, so this is going to be like x minus 1. And if you put things together, you're going to have x plus 5 divided by x plus 2 and x minus 1. So that means it is possible to actually have two different functions, and I can introduce the idea of the common denominator. Okay, so suppose that the goal is actually to integrate. Let's start from a basic example. Suppose we want to integrate something like this: x plus 5 divided by, in this case, let's do x plus 2, x minus 1 dx. Now, right in this form, guys, there's pretty much nothing you can do. If you do a u sub, it's going to fail. It's not going to work. Okay, or perhaps it leads to more complication. So then you have to think about the outside the box. So this guy is a fraction, right? So I begin to think about it. Can I split this integrand? Okay, you know what? This is the integrand, guys. This guy is the integrand. Okay, so the question is, can I actually split this integrand into two different fractions? Okay, the answer is yes. And if you back up a little bit, and that's really what we just have, we see that 2 divided by x minus 1 minus 1 divided by x plus 2 is actually this integrand. So I'm going to use that. So this becomes like I have a 2 divided by x minus 1 minus 1 over x plus 2. Then you do have a dx. Okay. Now this integrand is a rational function. Why? Because you have two functions divided, the quotient of two functions. Or you can say you have the quotient of two polynomials. That means you have a polynomial on the top, or you have a function on the top, and you have another function on the bottom. And think about this, guys. This becomes easy, right? Because you just integrate both sides, both parts, I mean. So you have 1 over x plus 2 dx. Okay, so how do you handle this sort of integral? Pull out your 2, you have 1 over x minus 1 dx minus integrate 1 divided by x plus 2 dx. Now this is 2. If you integrate this guy, what do you get, guys? This guy. And if you integrate this guy, what do you get, guys? Now remember, this is just going to be ln of the bottom, right? Because if you differentiate x minus 1, it gives you 1. And whenever you differentiate what you have on the bottom, if it gives you what you have on the top, remember, you just write the ln of the bottom. And you have the absolute value, right? So the same thing happens here. X plus 2. But I have plus c, which is my constant of integration. Okay, so that's one advantage of integration by partial fraction. You are able to split the rational function into sometimes two parts. Sometimes it can split into three parts or more, depending on what problems you're working with. Now, there are different things we have to observe, guys. There are different cases, and there are different ways we are going to approach them. Okay, so I'm just going to start now to begin to let you guys know what we're trying to do, because for different problems, you have different approaches. Okay, if you have a different problem, you have a different approach. Okay, so let's call this guy. Now remember, what function are we talking about? We're actually discussing a rational function f of x, which is equal to p of x over q of x, right? But there are a bunch of functions that can be written in this form, a lot of them. And sometimes you have this sort of functions, the degree of the polynomial on the top can be bigger than the degree of the polynomial on the bottom. The degree of the polynomial on the top might be less. So you have different cases, you have different observation. All right, so let me write observation 1. Now, keep in mind that we're studying this function that I have right here. We're studying this guy. Now, what happens if the degree of the polynomial on the top is greater than or equal to the degree of the polynomial on the bottom? Okay, so let me use a big Q in this case. What happens? And let me give you an easy example, guys. Suppose I have a function like, let's say you have x cubed divided by x. This is an example. The degree of this guy is a 2, is a 3. I mean, the degree of this guy is a 1. Okay, that's just an example. Now, whenever this happens, this actually that is f is improper. This is when we say the function is an improper. It's improper. Remember when we talk about improper fractions and all of those things. So in this case, this function is improper. Why? Because the degree of what you have on the top is bigger than the degree of what you have on the bottom, or at least, maybe equality. All right, so then you can actually write this guy. Remember, your function is f of x, and f of x is given by p of x divided by q of x. Whenever this happens, okay, you should write this your rational function in terms of s of x plus r of x divided by q of x. Okay, it's all going to make sense when we start doing an example. Okay, so apparently, what does this mean, guys? This actually means that we perform the division operation. Okay, so apparently this means we perform the division operation. Now, you might be curious to know, what is my, remember P and Q are polynomials, right? F of x is a function or it's a polynomial itself. So you might be curious to know, what is, S of x, R of x, so we need to give them a name other than say they are polynomials. So S of x is actually what we call the quotient. My R of x is what I call the remainder. And then the Q of x is what we call the divisor, right? Then P of x will call the dividend. Okay, so I'll give you an example, guys. Let's suppose that we have a function, suppose f of x is given by 3x cubed plus 2x, all divided by x plus 1. Suppose we have this guy. Now, what do I need to take notes, guys? I need to first check what's the highest degree of x on the top. It's a 3, right? Okay, so that means degree of 3x squared plus 2x is actually 3. This should be cube. That's the top, right? So what about the bottom? What is the degree of x plus 1? That's just 1. So clearly, I see that 3 is bigger than 1. So whenever this happens, observation 1 says perform a division operation, right? Perform a division operation. Okay, so this is going to be fun now, guys. I believe some of you remember this, little things you did. And you have this long division. All right. Over here, you have x plus 1. Remember, guys, how you do long division. So this first entry here is x. This guy is 3x cubed. So you want to do 3x cubed divided by x. You get a 3x squared. Then you multiply. So this is 3x cubed plus this is 3x squared times 1. You have a 3x squared. Okay, I hope you guys remember this. This is fun. So then you subtract, okay, so that you can eliminate this part. This guy goes out. But on the over here, you have like a 0x squared minus 3x squared. So you have a negative 3x squared plus 2x. We're not done. You do the same thing. Negative 3x squared divided by x. You're going to get a negative 3x. The negative 3x multiply this guy as well. It's 3x. So now I need to eliminate this guy. What do I do, guys? I got to subtract. Because when you have a negative 3x squared plus 3x squared, it goes to 0. And this guy is just 5x. Remember long division, right? So this guy, you have x divided by this guy, you still have a plus 5. So this is 5x plus 5. And this goes to 0. And over here, you have negative 5. And apparently, there's no other thing you can do right now. This is the best you've done. So what does this mean, guys? It means my function f of x, which is given by 3x cubed plus 2x, all divided by x plus 1, right? Can actually be written as, remember, what you have here is your quotient. So this guy is my s of x. This guy is my r of x. And this guy is actually my q of x. Okay, so, and it says you got to write it as s of x plus you have r of x over q of x, right? So that becomes 3x squared minus 3x plus 5. That's my s of x plus, what is the r of x? Negative 5. So I can just write this is a plus negative 5 all divided by, what is q of x? X plus 1. And this is the same thing as 3x squared minus 3x plus 5 minus 5 over x plus 1. Okay, so usually this is exactly what you do. All right, so what if the question pretty much was to evaluate this guy? Let's just say find what if we had this question? Okay, so what would you have done, guys? You're going to take this integrand, right? Because this is a rational function. You're going to split it just exactly what we just did so far, right? So at the end of the day, this is what happens. You have plus 2x divided by x plus 1 dx, right? This guy is equal to, remember, we've been able to split this integrand. We got 3x squared minus 3x plus 5 minus, you have a 5 right here over x plus 1 dx. Okay, so right now, what do? We can integrate. So I do have a 3 integral of x squared dx minus 3 integral of x dx plus 5 integral of dx, right? Then what about this part? You got a negative 5 integral of 1 over x plus 1 dx. So now without using the idea of this partial fraction, there's pretty much nothing you can do. Okay, so this is an important tool. So if you integrate this guy, you have a 3 times, you do have a s cubed over 3. You got a minus, this is 3. If you integrate this guy, you have s squared over 2. Plus, if you integrate this guy, you just have a x. Minus 5. Now, if you integrate this guy, what does it give, guys? Think about it. You have x plus 1 on the bottom. If you differentiate x plus 1, it gives you 1, right? So that means I'm just going to write ln of the bottom. So let's see, can we simplify? This guy takes off this guy. So I do have a s cubed minus 3/2 x squared plus 5x minus 5 ln of x plus 1 plus c. Amazing, guys. It's amazing. It's amazing how this works. So that's the first thing we can observe. We can observe that sometimes what you have on the top, the degree of the polynomial on the top is actually bigger than the degree of the polynomial on the bottom. So when that happens, think about it, guys. You got to do long division. Okay. Now we have another observation, which is the reverse of what we just did right now. Observation 2. What happens, guys, if the degree of the top is less than the degree of the bottom? Yes, it can happen. An example is just when you have, let's say, x over s cubed plus 1. The degree on the top right here is just x, right? And then degree of what you have on the bottom is 3. So it's clearly this case of observation 2. All right. So when this happens, what do we do? What's the action to do? Okay, then factor. You got to factor the bottom. When the degree of the top is less than the degree of the bottom, you factor the bottom. So factor or simplify Q. But you got to do that as much as possible. Okay, so that means you should be able to split it, to the least possible case. I'll give you an example, guys. Again, it's going to be an easy example. We have f of x equals x divided by x squared plus 2x plus 1. Okay, so let's remind ourselves the degree of the top is x, is just 1. And the degree of x squared plus 2x plus 1 is 2. Clearly, we can see that 1 is less than 2. And whenever this happens, you need to simplify what you have on the bottom. How can I simplify this, guys? You have a s squared plus 2x plus 1. Okay, remember, guys, this is just x plus 1 all squared. And x plus 1 all squared is the same thing as s plus 1 and x plus 1. So you got to simplify in that manner. Okay. So another thing, guys, we're still going to have another observation, which will lead us to, a couple of cases. Okay, we're going to have some other, that will lead us to some couple of cases. Now, I also need to mention, guys, that any polynomial can actually be factored to the point where every factor, right? Okay, so for example, this is a factor, right? Where every factor is either two things. Number one, the factor could be linear, okay? What does it mean for the factor to be linear? This means that I can have ax plus b. Linear in terms of what? The degree of x. The degree of x is just 1. Or the second thing it can actually be is what we call irreducible quadratic, okay? So what does an irreducible quadratic mean? It means that you have a quadratic equation that you cannot split. Okay, so let's say ax squared plus bx plus c with the discriminants. Do you guys remember discriminants? Okay, I guess some of you are like, oh my god, it's a long time. I get it, right? Okay, irreducible quadratic. So whenever you factor a polynomial, you can factor, to get to the point where you have two things are obtainable. It's either going to be linear or irreducible quadratic. I give you an example, guys. If I have my q of x, which is a divisor, right? X to the fourth minus 81. I can actually split this guy first into two parts, right? And x squared plus 9. But I can still split this guy. Remember, you have to factor as much as possible. Can I still break these guys down? Yes, I can break the first guy down to be x plus 3, x minus 3. Then this last guy, this guy is an irreducible quadratic. You cannot split it further. Okay? You cannot. All right? Makes sense, guys? Okay, so what do we know, guys? We can definitely back up a little bit to something we saw before. Before now, we saw that, in some cases, if you have a function, you can be able to write it in terms of these guys. Okay, so right now, I want to focus on this guy, this part. So then I'm going to say that we can express this guy, r of x divided by q of x, as a sum of partial fractions. Okay, so now we're getting it down into, a little bit more details. Okay, so we can express, this is CAN, we can express that guy as a sum of partial fraction. The example of such is, I can definitely write it. Remember, we said it could either be linear, right? It's a linear guy, or sometimes it could be of this form. AX squared plus BX plus C. You could have a power here. Okay, so let's just call it J, where your J can go from 1. So it all depends, right? It all depends. Okay, so now let's put everything we've learned so far, let's put it together in perspective. All right, so let me write in red just to provide first a very tiny summary at this point. We're not done yet. So the tiny summary, let me just write here, tiny summary. Okay, we say if you have this guy, okay, so different things are obtainable. We say it's possible that the degree of P is bigger than or equal to the degree of Q. When this happens, what do you do, guys? You do the long division, right? We've said that when the degree of P is less than the degree of Q, what do we do, guys? We got to factor Q. And the last thing we mentioned is that when we have a situation with R of X divided by Q of X, you can actually be able to write this guy as either something like this or something like this. X squared plus bx plus c to the power j. Remember, your j is non-zero and your j is non-negative, right? So it's better I write it this way. So j is greater than or equal to 0. greater than or equal to 1. Yeah. Okay, so that's like a tiny summary as we proceed to other part of the work. So now we're going to start discussing some different cases that will help us going forward. So let's call this guy case 1. In case 1, what are we trying to say here? Okay, remember, our goal is still on this guy, on the rational function, right? So what happens when the divisor is a product of linear factors? What do you mean by product of linear factors? This is exactly what I mean. That means we do have a1 of x plus b1 multiplied. That means the highest power of x is just 1. Okay, means in all these cases, these guys are gonna be 1. Okay, b2. You can continue on and on to have ak x plus bk. The power on x is still 1. Now, when this happens, we often say that, okay, we have no repeated. Okay, in this case, we're saying that we're assuming we don't have a repeated factor, I mean. Okay, no repeated factor. Okay, and no factor is a multiple. Okay, so let's say it's a constant multiple. No factor is a constant multiple of another. Now, what are we saying? We're saying that we're avoiding cases where you have x plus 1 and x plus 1. This guy and this guy are repeated factors. So we're saying we don't want this case. Case 1 does not deal with this kind of issues. Okay. So if this happens, if I have this q of x, which is a product of linear factors, what happens? What's the implication? The implication, okay, so the implication for us is that I can be able to write my remainder, the division of my remainder and my divisor, to be equal to, you have a1. This is just kind of, bringing back to light your partial fraction, guys. Okay, a1 of x plus b1 plus a2 over a2 of x plus b2. And, so we're of course, we're doing well to introduce the theories behind this guy, and then we apply it. Okay, so it gets a lot interesting when we move to the point of application. It gets a lot interesting. Okay. Okay, let's do an example, guys. Example. Now, if you do have an integral of x squared plus 2x minus 1, all divided by, you have 2x cubed plus 3x squared minus 2x dx. Okay, I have this situation, guys. What do I do? The first thing I need to check is the degree of the top. What is the degree of the top? Okay, so let me just write degree of the numerator. Okay, so what is the degree of the numerator? It's 2, right? What's the degree of the denominator? It's 3. Now, of course, 2 is less than 3. Once this happens, what did we say, guys? We say we're going to factor q as much as possible. Okay, so for this purpose of learning, let me just divide this guy to step. Let me say step 1. Factor q. And how do I know I should factor q? Because of the situation. 2 is less than 3. Okay. All right, so 2x cubed plus a 3x squared minus 2x. If you factor this guy, okay, what do you expect? Now, remember, what do I know, guys? I know x is common to these guys. I can pull out x at first. So I'm left with 2x squared plus 3x minus 2. But is the job done yet, guys? Not quite. Remember, factor q as much as possible. Okay. Can I actually do another kind of factorization? Okay, yeah, definitely. This is x, but this 2x squared plus 3x minus 2 actually splits up to x plus 2 and 2x minus 1. Remember your college algebra, right? So again, for the purpose of learning, let me call the next step, step 2. So what is step 2, right? Okay, I'm going to write P of x over Q of x in partial decomposition form. Okay, so I'm going to write the guys in partial decomposition form. All right, so what does that mean for us? I have a s squared plus 2x minus 1 divided by, you got 2s cubed plus 3x squared minus 2x. In partial decomposition form, remember first, I know the guy on the bottom actually splitted to be x plus 2, and 2x minus 1. Take a look, guys. Think about the bottom. What kind of factors are these on the bottom? Are they linear factors or quadratic? All right, so these are linear factors. Why? Because the power on the axis are just 1. So once that happens, you write a over x plus you got a b over x plus 2 plus c over 2x minus 1. Okay, so you got to remember what we're trying to do, what we're trying to achieve. This should be a p, guys. That should be a p. Okay, so what are we trying to do? Remember, this is a1, right, plus a2 plus a3. So, and that's up to ak, and that's exactly what is happening here. But in this case, we just say a, b, and c. If you like, you can do a1, a2, a3. They are just constants. So apparently, guys, what happens? Okay, so I need to generate this guy as a single fraction. Okay, so I need to be able to write it as a single fraction. Step 3. Okay, right. Step 2. As a single equation, I mean, not fraction, as a single equation. How do you write this guy as a single equation? Think about it, guys. Okay, to write this guy as a single equation, I need to multiply by, in this case, I multiply this guy by x, by the whole of this guy, the whole of the q of x. S plus 2, 2x minus 1, right? I need to multiply each of them by q of x. Okay, so think about it this way. So if I do that kind of multiplication, guys, what do you think? This x is going to short out this x. And over here, this x plus 2 will short out this x plus 2. And over here, this 2x minus 1 is going to short out this guy. Okay, so equivalently, that means x squared plus 2x minus 1 is just going to be equal to, in this case, it's just going to be equal to, you have a, x plus 2 and 2x minus 1 plus b, you got to have x, 2x minus 1 plus c, got x, x plus 2. Okay, so why is that important? You know, I just want them to have the same thing on the bottom. Got the same thing on the bottom. So now we need to determine what the values of our constant are. Okay, I need to determine the values of my constants. I need to determine the values of my constants. Now let me give you a trick when you get to this point, okay, about what to do. Okay, so the trick about what to do is remember that my Q of X actually simplified to be this guy. Okay, so think about it intuitively by setting this guy to 0. If I set this guy to 0, that means my X is going to be 0. My X is going to be -2. And my X is going to be 1/2. Okay, when you set it equal to 0. Now, if you guys remember what you learned in partial fraction, okay, apparently you remember that you can do the cover-up method, or perhaps you can do the comparing coefficients. Okay, you can do cover-up method, or you can do comparing coefficients. So how did I get this, guys? I just set this guy equal to 0. Okay, what did I set equal to 0? I set this guy. And then what do? The first thing is when X is 0, what happens? When X is 0, let me call this guy equation star. Okay, when X equals 0, so you're going to plug X equals to 0 in equation star, because you need to determine the values of these constants. All right, and if you determine the value, then you can integrate. Without the value, then it's more like you're not doing anything, right? It's like a half job. If I plug in X right there, you do have 0 squared plus 2 times 0 minus 1 equals, you have a, this is 0 plus 2, right? You got a 2. This is going to be 0 minus 1, you got a -1, plus that guy becomes b times 0 plus c times 0. Okay, on the left-hand side, I have a -1. On the right-hand side, this guy goes to 0, this guy goes to 0, -2a. What does this mean, guys? It means my a is just 1/2. So I'm done with this part, right? What about when X is -2? When X is -2, you do the same thing, guys. You plug that guy X equals -2 in equation star. Plug this guy in equation star. If you plug this guy in equation star, the left-hand side becomes a 4 minus 4 minus 1. The right-hand side becomes a times 0 plus b times 0 plus you have c. You got a -2 and then -5. Remember, you're plugging it where? In equation star, in this guy. In this case, now my left-hand side is going to be a -1. 4 minus 4 gives me 0. 0 minus 1, you got a -1. This guy gets to 0. This guy goes to 0. I'm going to be left with 10c on this side. Now I can actually determine the value of c. -1/10. Makes sense? So the last part, when X is what? I think that was a 1/2, right? Yes. So we're done with this part. So we're left with when X is 1/2. When X is 1/2, what happens? I got to plug X equals 1/2 where? In equation star. So if you do the plug in the left-hand side, you got a 1/4 plus 1 minus 1. And then you have 0 times a times 0 plus you got b times 1/2 times 5/2 plus c times 0. You can plug it and see that these values are correct. This guy goes to 0. This guy goes to 0. The left-hand side, you got a -1 plus 1 minus 1 gives me 0. So over here I have a 1/4. And over here I have a 5/4b. Amazing. So now I can find the value of b. My b is just going to be 1/5. Okay, so far so good. What do I know, guys? I do know that my A is 1/2. My B is 1/5. And then what about C? My C is actually, what was that? That was -1/10, okay? All right, so now we move to step 4. Now we're going to move to step 4. In step 4, what are we trying to do? Now, in step 4, now you remember that we had an equation. We had this guy. We had integral of s squared plus 2x minus 1 over 2x cubed plus 3s squared minus 2x, right? We equated this guy to a divided by x. Remember that? Plus, of course, I got an integral here. B divided by, that was, 1 second, let me back up to be sure. That was x plus 2. Okay, cool. And then plus c divided by 2x minus 1, you got a dx. So in step 4, you got to plug in the values of a, b, and c. So if you do that, guys, that means you have a s squared plus 2x minus 1 divided by, you got a 2x cubed plus 3x squared minus 2x. This is just the left-hand side, right? Integral. But what is a? A is 1/2. So apparently, that means I have a 1/2 on the top. 1/2 here. A is 1/2, right? Divided by x. What is b? My b is 1/5, right? What is c? My c is -1/10. All right. So then this is now you can see how partial fraction helps us to leave the idea of a huge complication to a very simple thing. So if you integrate this, you want to integrate this guy, you factor this guys, right? Then this is a plus 1/5, 1/s squared plus 2 dx, -1/10 integral 1/2x minus 1 dx. Okay, so over here, this is a 1/2. If you integrate this guy, this is just ln of this guy, right? Plus 1/5. If you integrate this guy as well, this is just going to be ln of x plus 2. All right. So, but in this case, are we done yet? The answer is a no, right? Okay, so over here, what do we do? So over here, I got -1/10. Now, but if I differentiate this guy on the bottom, guys, I'm just going to have like 2. But what you have on the top is 1. Do you remember how you introduced this trick? The 2/2 trick. Okay, so this is like, okay, 2 on the top. Let me put 2 on the bottom. Okay, remember the 2/2 trick? That's why I have it in red. 1/2 ln of this guy. plus 1 over 5 ln of x plus 2. All right, so minus over here, I got a 1 over, this guy becomes 10 times 2, 20. All right. So what is this guy going to be? 1/2 ln of absolute value of x plus 1 over 5th ln of x plus 2 minus 1 over 20. Now, if you integrate this guy, you're just going to have ln of 2x minus 1. Then you have a plus c. Okay, makes sense, guys. So in this session 7.4, it depends on what the problem is. Some problems are definitely going to demand more work. They're going to be required to do more work. Or some could be a little lesser than this, but if you follow through what we've been doing so far, you know, it makes a lot of sense, right? Everything we've been doing so far does make a lot of sense. Okay, so we got the constant, then we put it in. When you pull in the constants, you have the situation. Yes, you have this guy. Then you bring in this trick, this 2 over 2 trick, because you need what you have on the top to be a 2. But you know 2 divided by 2 is just 1. So you just introduce that trick. Okay. So that's the first case, that can actually happen. So we have another case. We're going to look at, another case. Let's call the guy case 2. In case 2, what is our focus, guys? In case 2, what happens when my Q of x is a product of linear factors, some of which are repeated? Remember, in case 1, we don't have repeated factors. But right now, what if we have repeated factors? How do we approach it? Okay. Let me give you an example. It's best to just right now go directly to an example. So in this example, if you have integral x to the 4th minus 2x squared plus 4x plus 1, all divided by, you got a s cubed minus s squared minus x plus 1 dx. Okay, I need to actually integrate this guy. What do I do? How do I approach this? That becomes the question I want to answer, right? Let us see. So what do I need to pay attention to? What is the degree of the guy on the top? It's a 4, right? What's the degree of the highest degree of the guy on the bottom? 3. 4 is bigger than 3. Remember, when you have the situation of the highest degree on the top bigger than the degree on the bottom, what do you do, guys? Think about it. Long division. Okay, so we got to do a long division on this guy. X to the 4th minus 2s squared plus 4x plus 1. S cubed minus x squared minus x plus 1. Okay, so how do I approach this guy? The first entry is x cubed. The first entry is x to the 4th. You start by doing x to the 4th divided by s cubed. You just have x, right? Multiply, you have x to the 4th minus s cubed minus x squared plus x. Now, I need to get rid of the common guys now. You have x to the 4th is common. That means you have to subtract. If I do subtract, this guy goes off. So right now I have a s cubed minus s squared plus 3x plus 1 right? Okay, so the guy here, the first entry is a s cube. This guy is a s cube. S cube divided by s cube, you have +1, right? You do a +1. Okay, so that means if you multiply, you have this guy. So these guys are common, right? How can I get rid of this guy? I got to subtract. If you subtract, guys, this guy goes to 0, this guy goes to 0. Okay, 1 minus 1 goes to 0, so you're left with 4x. Okay, so that means easily, guys, I can see that this guy divided by s cubed minus x squared minus x plus 1 is going to be equal to s of x. That's a quotient. What's the quotient right now? You have x plus 1. What is the remainder? Remainder is 4x, and then the divisor, s cubed minus x squared minus x plus 1. Okay. All right, so now I need to pay attention to this part. What is the degree of the guy on the top? Okay, it's 1, right? What is the highest degree of x on the bottom? It's 3. So now I have a situation with 1 less than 3. Hey guys, what do we do? Remember, you got to factor q as much as possible. That means I have to factor this guy on the bottom as much as possible. So let's call it step 2. Factor this guy as much as possible, right? If I factor that guy, you got s cubed minus x squared minus x plus 1, which is equal to, if you factor this guy, I bet you might have to remind yourself how to do this kind of this type of factorization. Okay, and then this guy is just, I can write it as s squared minus 1 and then x minus 1. Okay, but are we done here, guys? Not quite. S squared plus minus 1, you can definitely write that guy as x minus 1, x plus 1, and then you have this guy. What can you see clearly, guys? Clearly, you can see that this guy, this is a minus. The same thing as x plus 1, x minus 1, x minus 1, that's a square. Okay, can you see the idea of the repeated root right now? This guy is the same as this guy. Okay, so step 4, in step 4, we're going to try to bring things, step 3 right now, we're going to try to bring things together. So remember we're actually going to do 4x over this guy, right? S cubed. This is a minus x squared minus x plus 1. And we found out that this guy can be written as x plus 1 and x minus 1 all squared. But in this case, because this is a repeated root, what do? I equate in terms of partial fraction, a divided by, the linear part is always just going to have a constant by itself, a. But this guy, it's linear though, but repeated. So that means I'm going to do b over x minus 1 plus c divided by x minus 1 all squared. Amazing, right? So you see that there's a difference right now. Okay, so you have, whenever it is linear and repeated, you give a constant to the first part, then you give another constant to the whole thing. So that's why we have like b divided by x minus 1. Then you have a plus c divided by x minus 1 all squared. Okay. So it's getting more interesting, more and more interesting. So let's see, guys. Let us see. Let's back up a little bit. So now remember that this guy, let's call the whole of this equation. Let me paint this guy in blue. Let's call the whole guy in blue equation star. Now remember that we're only actually dealing with the red portion so far from equation star. Why? Because this guy x plus 1 is very easy to integrate. So because it's very easy to integrate, we just hold up a second and say, okay, I'm going to be back to you. Let me deal with the tough guy first. Okay, so we're dealing with the tough guy. We're going to be back to the easy guy. So we're still on the tough guy. So right now in step 4, what do we want to achieve? We got to pull up a common denominator, right? Okay, so from step 3, obtain a single equation. Obtain an equation without fraction. So what does this mean, guys? The same thing we did in the previous example. You got to take rid of the bottom. How do you take rid of the bottom? You can multiply. So let's see. What are we multiplying by in this case? X plus 1 and x minus 1 all squared. X plus 1 and x minus 1 all squared. And x plus 1, x minus 1 all squared. Okay. All right. So, but remember, the same thing we did before. In this case, our q of x is x plus 1, x minus 1 squared. Remember, we said this guy equal to 0, right? Remember that, guys? If you set that guy equal to 0, why do I need to set it equal to 0? Because I want to make life easy, right? Okay. And then you can still do x equals 0. Okay. So over here, intuitively, you get these two guys from here, right? But we're looking for factors such that we can easily solve these guys. Okay, so that's why we have a 0. If you just have x equals -1 and x equals 1, you will only be able to find two constants. And how can you get a third guy? You can actually get a third guy by setting x to be 0. Okay, so that's why we have that guy, x equals 0. So what happens when x equals 1? Oh, okay, before we begin to plug in that guy, when you multiply by the red guys I have on top, I'm going to end up having 4x plus a x minus 1 all squared plus b x minus 1 plus c x plus 1. So when x equals 1, what happens? Plug in 1, you have a 4 here, a times 0 plus b times 0 plus c times 2. This means that my c is just going to be 2. Okay, so when x is a -1, what's going to happen on the left-hand side? You got a -4. On this right-hand side, you have a -2 all squared, plus you got a b times 0 plus c times 0. And this means my a is going to be -1. Okay, so what are we doing, guys? We're plugging these guys in this equation. Let's call it star star. Equation star star. And the last guy, x equals 0. If I don't have x equals 0, then how do I find my b? Yes, you can still find your b. How? Plugging a and c in equation 2. But make life easy, just go to 0. This means 0 equals you're going to have a a to negative 1 squared plus you got a b times negative 1 plus you got a c times 1. So, but already I know my a and b. My a is negative 1 minus b. What is c? I mean, I already know my a and c, not b. B is what we're looking for, right? C is 2. Apparently, guys, my b is just going to be 1. Make sense? So that's step 4. What about step 5? In step 5, we have to put things together, okay? Now plug in your constants, right? Divided by, you have x cubed, x squared minus x plus 1 dx. If you plug in this guy, remember, this is back to equation star. Remember, what is equation star? The blue guy, right? The blue box. Okay, so in the blue box, remember we had this guy, s plus 1. And then, okay, get a is negative 1, right? So I have a plus negative 1 divided by x plus 1 plus, what is the value of b? B is just 1. 1 over x minus 1. What is c? C is 2. Amazing. So now it's now a very easy fraction and you can just integrate. So this is going to be integral of x dx plus integral of dx, and that's this guy, minus integral of 1 over x plus 1, that's this guy, plus integral of 1 over x minus 1 dx, that's this guy, plus you got a 2 integral of 1 over x minus 1 all squared dx. Okay, so you have x squared over 2 plus, if you integrate this guy, you got an x. If you integrate this guy, this is just ln of the bottom, okay? Because if you differentiate x plus 1, it just gets 1, and that's what you have on the top. Ln of x minus 1 plus, now over here we have 2, 1 over x minus 1 all squared dx. But remember, how do you solve this guy? I'm not going to show you guys, but I believe it's what you can do. This guy, to integrate this guy, remember you do a u sub. Okay, you do a u sub of u equals x minus 1. So at the end of the day, you're going to get all of this guy. Okay, if you integrate this guy, of course, you have a 2 up front. It's going to give you a negative 1 over x minus 1. Then you have a plus c. So I can just simplify a little bit further. Now, do you remember the law of logarithms? I can actually, that helps me to combine these guys. ln of, you got x minus 1 on the top, x plus 1 on the bottom, minus 2 over x minus 1 plus c. And that's it. Interesting, right? Okay. All right, so I'm just going to consider one more case and then we're done. Okay, I'm just going to consider one more case, guys. Let's call it case 3. Now, in case 3, what happens when my q of x Q of S is a divisor, right? Do you remember that? Contains irreducible quadratic factors. None of which is repeated. Let me give you a simple example first, and then we'll do an integral problem. You have x divided by s minus 2, s squared plus 1. Now, this you equate it to a, right? What kind of factor is this guy? Linear, right? Because this guy is linear, this guy is just going to be a. This guy is quadratic, right? Quadratic and irreducible. That means you cannot split it up into two. So whenever you have a quadratic irreducible, you just do bx plus c, s squared plus 1. What about this guy? Quadratic and irreducible. You cannot split it. So that means you have dx plus e. So it's all going to make sense when we do an example right now, guys. In this example, our main interest is this guy. Okay. What do I do in this case, guys? Again, where do I start from? You check the degree of the top. Degree of top is 2. The highest degree of top is 2. The highest degree of bottom or denominator is 3. 2 is less than 3. If this happens, guys, what do? Remember, you factor Q as much as possible. So I start by factoring this guy. X is common, right? We have x, s squared plus 4. Can you do anything else? No, guys. This is linear, but this guy is quadratic and irreducible. So that means I have a 2s squared minus s plus 4. Now, resolve this guy into partial fraction. That becomes a. This guy is linear, so it's just a over x. But this guy is quadratic irreducible, so you have a bx plus c over s squared plus 4. So we're going to do what we've been doing before. Avoid the fractions. If I need to avoid a fraction, what do? Multiply by s squared plus 4. So that means your left-hand side is going to be this. Your right-hand side is you're going to have something like this guy. Okay, if you distribute your right-hand side, you're going to get a s squared plus 4a plus bx squared plus cx. This is a s squared, this is a s squared. You can factor those guys. You got a plus b x squared. Then you got cx plus 4a. Take a look at this part carefully, guys. Remember, it's irreducible, so you cannot think about the idea of setting q equals 0. So, but what can I say? I need to compare both sides. This guy has a s squared, this guy has a s squared. Comparing both sides, you have a plus b equals 2, okay? This guy has x, this guy has x, so that means c is -1. This is 4a, this is 4. Those are the constants, so that means my 4a equals 4, right? Set the constants equal to themselves. So apparently, this guy is going to be, on this case now, I'm going to have you have a plus b equals 2, right? So let's start from the bottom. A equals 1, right? C equals -1. So this means that my b is 2 minus a, which is 2 minus 1 equals 1. So I know what a is, I know what b is, I know what c is. So you just go ahead and plug it in. So we now have a 2x squared minus x plus 4 over x cubed plus 4x dx, which I can now write as integral. What is a, guys? A is 1, okay? 1 over x. What is b? B is 1, so you have x minus 1 over. Now, why do I have a minus 1? Remember, we had bx plus c. That's a 1x minus 1 dx. All right, so let's see, guys. So this is integral 1 over x dx plus integral of x minus 1 over x plus 2, x squared plus 4, I mean, dx. Okay, let us see, guys. This is equal to, if you integrate this guy, you get ln of absolute value of x. That's the ln of the bottom. Do you remember, guys, if you have a plus b divided by 2, this is the same thing as a over 2 plus b over 2. So I'm going to apply this principle on this part. So that means I'm going to have x divided by x squared plus 4 dx minus 1 over x squared plus 4 dx. This part is easy to get, guys. For this part, I got to do some work, okay? X over x squared plus 4 dx. Okay, what work do I do, guys? How do you integrate this guy? Do you remember u sub? Okay, you just let u equals x squared plus 4. And then du is going to be 2x dx, which means my dx is du over 2x. Okay, so that apparently means that this guy becomes a 1/2 u du. And this is actually 1/2 ln of u plus, let's say, c1, which is just a constant, right? But what is u? U is exactly x squared plus 4. So can I plug in this red back to where it belongs? Okay, the answer is apparently yes. Okay. Let me write this guy in green. Think about this. If you integrate this guy, what do you get, guys? If you guys remember this guy, if you integrate this guy, it's going to give you arctan, right? X over 2. This is just a standard. If you remember 7.3, then that's not going to be a problem. Okay, but it's going to be a 1/2. I missed a 1/2 up front. Okay, so now let's go back, putting everything together. 2x squared minus x plus 4 over x cubed plus 4x dx. This guy is going to be equal to ln of the absolute value of x plus 1/2 ln of x squared plus 4 minus 1/2. Then you have arctan, right? Plus c. And that's how beautiful it can be. Okay. I mean, that's how beautiful the process can actually be. Very beautiful process. Okay. So I'm just going to introduce case 4, but we're not going to do a lot about that. Just going to introduce it, guys. I'm going to tell you what case 4 could be. Okay. Case 1, we had the linear factors, right? Case 2, we had linear factors but repeated. Okay, so and then case 3, we had quadratic and irreducible. So case 4, do we have the question like, okay, what if you're quadratic, or what if you are repeated irreducible? What happens? Okay, so case 4 is when Q of X contains a repeated irreducible quadratic factor. Okay, so that way we say if Q of X has the factor ax squared plus bx plus c to some certain power r, okay? Of course, the discriminant, if you guys are familiar with irreducibility, the discriminant has to be negative. And that's when you say you have a complex root, you don't have a real root, okay? Okay, so then the partial fraction decomposition of Q has the factors. I'm not going to solve the example, but I'm just going to show you what this means. You know, this is like a theory, but just going to show you guys a2x plus b2 is ax squared. I see I made a mistake here. This is as squared plus bs plus c. This is going to be to the second power okay. So an example, a good example is this, guys. If I have an example, and that's where I'm going to stop. If I have 1 minus x, for instance, plus 2s squared minus s cubed, all divided by x s squared plus 1 all squared. Now, I will take a look at the bottom, guys. I know this first part is linear. I have no problem. Linear guys are the easiest guys. But I know this guy is quadratic. It's quadratic. It's irreducible. But there's a problem, guys. There's a square right here. That means it's repeated. So 3 things in this case. So if I want to resolve this guy into partial fraction, it's going to be a over x plus the fact that it is quadratic and irreducible. So this guy becomes my first, number 1. Number 2 guy with the constants. And then this is going to be, whole of this is going to be number 3rd guy. So number 2 guy, when it is quadratic and irreducible, what do you write? You write bx plus c. Now, the fact that it is now quadratic, irreducible, and repeated, what do? You do a dx plus e divided by, and then you solve for a and b. Then solve for a, b, c, up to d. So, but of course, this guy is much work to do. Okay, makes sense, guys. So this is, you know, the whole thing about using partial fractions to actually attempt integrating rational functions. Okay, I'm quite sure you guys may, you know, if you feel free, the video is there. If you need to see this video more than one time, why not? All right, guys.